Oh, hi. I'd like to start off this little gas treatment with a demo. I brought in a large test tube. Inside this test tube is a little rubber stopper, and I'll describe its purpose in just a moment. And I'd like to mimic what occurs inside of an internal combustion engine, or a car or a lawnmower or a motorcycle engine. Many cars have 4, 6, 8 cylinders. There are some Jaguars and Ford V10 engines that have more than 4, 6, or 8 cylinders. This is just one cylinder, and I'm going to have a little detonation. I'm going to put in some gasoline, and I've got it figured out. Practice over the years. I'm going to put in 19 drops of gasoline. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And some people are thinking, well, that's not very much, but trust me, it is enough. Some people are thinking, put in much, much more, but that would be bad. That wouldn't be like a good explosion bad. That would be flooding the car, flooding the system. The balanced reaction for this is shown here on the board. Octane, C8H18 liquid, is a major component of gasoline. It's going to react with oxygen in the atmosphere to produce carbon dioxide and water. And I have this listed in the gas phase because, as we'll see, this takes place at a high temperature. Now, I'm going to put a rubber stopper on the top of this for a moment and bounce this little rubber stopper back and forth. And I'm acting like a carburetor. I'm mixing the fuel in the air, and there's no more liquid left. It's vaporized, it's all in the gas phase, and hopefully nicely mixed. Now in an automobile, what will happen is a spark plug will go ahead and be set up so that the spark is inside the cylinder, and you get a little explosion, and work gets done by moving pistons, things like rods and drive shafts and axles and wheels. Here I'm just going to drop a match in. So put on some safety glasses and drop a match in from the top. Let me drop a match in from the top and have a nice little detonation. Nice sound. Oh, hi. On the worksheet page for Chem 121, there's a problem, and that is the generation of carbon dioxide from octane. And I'd like to work through most of that problem with you. I went ahead and put up on the right board here a balanced reaction for the combustion of octane. Octane is a liquid. It's a major component of gasoline, lawnmowers, motorcycles, automobiles, generators. Oxygen comes from our atmosphere, and out of the tailpipe, carbon dioxide gas, and that's a great concern to us. And water, and I listed in the gas phase, like water or steam is coming out of the tailpipe because of the temperature of the reaction. Now, if somebody goes ahead and drives a little economy car like a Toyota or Honda, let's say about 30 miles, I'm estimating that they're going to consume about 3,500 grams of octane or gasoline. Very comparable to like saying, well, I get good gas mileage and burning up about a gallon of gas. Now I'm going to ask the question, how many liters of carbon dioxide are produced? So you can envision a 2-liter bottle, like a soda bottle, of carbon dioxide. Well, how many liters of CO2 are coming out of the tailpipe if we drive, say, 30 miles and burn up a gallon of gas or so? So I'm estimating 3,500 grams. We're going to do a 3-step problem here. Change it into moles. Come on over here to the right underneath carbon dioxide using our balanced equation to moles. Now in the past, we've converted that to grams, asking the question, how many grams of a product are made? But now that we're doing gases, we're going to use moles and use PV equals nRT under reaction conditions and say liters. Step number 1. Grams to moles calculation. Step number 2, using the balanced reaction to calculate the moles of our product, CO2. Let me put an X through that route. That was like last chapter's problem. Moles back up to grams. Let's use PV equals nRT and calculate liters in step number 3. So step number 1, we have 3,500 grams of C8H18, and we'll convert that into moles of C8H18. Formula says 8 times 12.01 plus 18 times 1.0079 or so. I'm going to round that to 114 grams per mole. You can use a much better number if you'd like. So 3,500 grams divided by 114 grams per mole give us 30.7 moles of octane present. Let me pencil that in. 30.7 moles into our flow chart. Our nicely balanced equation for step number 2 says we can convert the moles of octane into the moles of carbon dioxide. Would you please take a moment and fill in our conversion factor with the appropriate units and the appropriate values? From the balanced reaction, we will get moles of octane. That will be necessary on the bottom, so moles of octane cancel. From our balanced reaction, moles of CO2. That'll go on the top, so moles of CO2 are produced. This balanced reaction says 2 moles of octane produce 16 moles of CO2. If you'd like to make a division by 2 on that whole reaction and keep a fraction in there, your reaction would read 1 mole of octane makes 8 moles of CO2. Everything works, numbers turn out the same. So 30.7 times 16 over 2, and I'm going to write down 456 moles of CO2 and pencil that into the flow chart. The last step is going to involve PV equals nRT. That problem will make some assumptions over what the pressure is, what the temperature is. Let's go ahead and take a look. What would we like to solve for? We're interested in the liters of CO2. Let's solve for the volume. Rearranging, we want the volume all by itself, so we're going to divide both sides of the equation by P, the pressure. The P here will go away, and we'll have division by P on that side. V is equal to nRT over P. N, the number of moles, goes in first. We have that now. 246 moles of CO2, 246 moles of carbon dioxide gas. We always have R. In this equation, we'll use our old standby, 0.0821 with the units of liters times atmospheres over moles times kelvins. Now the temperature is up for debate. Temperature of an internal combustion engine, a car engine, a lawnmower engine, is really quite hot. One could argue, though, that the carbon dioxide comes out hot and then it will cool. So let's use the conservative number. Let's go ahead and say it's going to cool down. It's going to come down to a smaller volume. Let's use a nice day outside, somewhere like in the low 70s, and say, hey, it'll end up at room temperature, 298 or so. The pressure, wherever you live in the world, the atmospheric pressure is going to be very close to 1 atmosphere, plus or minus a little. If you've got a big weather system coming in, this might change a few percent, but let's stick with 1 atmosphere. Units cancel nicely. Moles cancel, kelvins cancel, atmospheres cancel, and we're left with liters. The volume of carbon dioxide produced from combusting approximately 1 gallon of gas. Oh, this is going to be interesting. I calculate it to be 6,000. Let me write down 6,000 liters. We've made some estimates. Burn 1 gallon of gas, like think of a 1 gallon gas tank or a 1 gallon milk jug. It's a liquid. We're producing quite a bit of gas because the molecules are spread out. Carbon dioxide gas has carbon in the center, black, oxygens on the outside, reds, a couple of double bonds that we'll talk about later. This thing's really traveling fast, hundreds of miles an hour, we know, and we're producing 6,000 liters, or think of it as 3,000 2-liter bottles. Pretty incredible.